where we're going to be having talks about the characterization and mitigation of foregrounds. So before we start, and I pass the word to Saurabh to present the results. I would like to tell everyone that you could either put questions on the Q&A or on the chat or on the Slack channel. And this is the third session. So the second day is the first session of the second day. So it's going to be 2A. So I'm going to be checking all of those. So to pass on questions. Also, I see that people are coming online. Maybe, I don't know if I should give it another 5 minutes for more people to come online. So let's give it another 1 to 2 minutes, and then I'll cut the break. I think the results of Saurabh would be something that interests a lot of people, although the numbers seem to be quite stable. Yeah, the numbers quite stable. So, okay, I think, yeah, the numbers have stabilized. So welcome everyone, and I'm pass the word to Saurabh Singh, who's an invited speaker, is going to tell us about, from the Raman Research Institute, and he's going to tell us about on the detection of cosmic dawn signal in the radio background. And I pass the word to you. Thank you, Saurabh.
Thanks. Yeah, let me try sharing a screen. All right. Can you see the screen? Okay.
Yes.
So hi everyone. So today I would be talking about the latest results from SARAS-3 experiment and the inference that we have drawn on the cosmic dawn signal. And the key takeaway is that we have refuted the presence of the flat profile, which was detected by Edge's collaboration as was interpreted to be the cosmic dawn signal. And it recently was just out, the accepted version, and I encourage everyone to go and check it out. Before I go into the details of the instrument and the analysis, big shout out to the entire team members who have really made all of this possible with a lot of help from different facilities at RRI. And with that, let's get started. So the motivation of SARAS-3 observations were to cross-verify the claim of the edges detection that happened in 2018. And specifically, we are looking for this specific signature, which is a flat Gaussian with an amplitude of 500 millikelvin. And the question was that if we repeat this at a very different site with such a different instrument, can we cross-verify this? So SARAS as an experiment has its own series of different evolution, changing in its antenna designs, in its calibration, in its observing environment, and also the observing medium. And I'll touch upon briefly in the later slides about this evolution. But overall, the design philosophy of this radiometer has been to preserve the spectral smoothness of the foregrounds. So we all know that one of the primary challenges in these experiments is to separate out the foregrounds from the 21 centimeter signal, which is a huge dynamic range problem. But we know the spectral smoothness of the foregrounds is something we all take advantage of. So SARAS-3 is designed so that the instrument response itself does not introduce spectral structures that mimic the 21 centimeter signal. So we have a very mild frequency dependence of the beam, as well as what we call as maximally smooth response of the system itself, which basically ensures that along with the foregrounds, all the different components except the 21 centimeter signal continue to be spectrally smooth and can be represented by a few modes. And this is what the system looks like. It's a single antenna system with a monopole antenna as the electromagnetic sensor. Along with it, we have an analog receiver that sits just below the antenna. And this is one part of the system. Separated by around 150 meters, we have rest of the electronics followed by the digital spectrometer. And I'll just briefly touch upon a few of these subsystems before going into the deployments. So the first is analog receiver. It's basically a decay switch radiometer where we use a very standard noise source for calibrating our system bandpass. And later in the chain, we split down this signal into two different arms. And therefore, this is like a pseudo cross correlation spectrometer. And the advantage that we get is a lot of common mode systematics, the systematics that are added later in the chain get canceled out. And another thing is it's just miniaturization. So as you can see on the plot on this figure right here, that the entire thing has been compactified to be just like a 10 centimeter system. And with that, any kind of standing waves that occur due to the reflections are basically spectrally smooth and occupy a very small fraction of a complete sinusoid. And given the remoteness of these deployments, we basically run off the entire systems on batteries, and therefore we do not depend on any AC power. The digital system is one of the noisiest element, and therefore it is caged in this nicely shielded Faraday cage. This is a 10-bit ADC platform, which has been in-house developed at RRI, and this gives us around 61 kilohertz frequency resolution and 67 milliseconds time resolution, which is required for us to be doing fine level RFI excision. And basically, we also window the channels so that the inter-channel leakage is suppressed by more than 80 dB. So with this system in mind, we did the first deployment in 2018, and this was done in Trans-Himalayan ranges in India. These observations lasted around 2 weeks with two very different antennas, both being monopole, but with very different radiators, as you can see on this plot. While the observations were very smooth, we were limited by a specific systematic that occurred because the antenna was also tracking or basically sensing the ground radiation. And at the wavelengths at which we operate, we were not just sensitive to the top level of the ground, but several meters below it. So unless we had the full information about the soil properties, their frequency dependence, and also their profile with the depth, it was very difficult for us to basically address this specific systematic that limited us from reaching the sensitivities that we required. So the next question was, how do we deal with such a problem? And one of the natural solutions was to deploy this on lakes rather than on land, because this would provide us a very homogeneous medium, and therefore it would be a much easier system to model, because really the observing environment is very much the part of the antenna. So with some criteria in mind, we had an extensive survey of the sites, and we finalized 2 lakes in southern India that are shown here. And that's where we did our second round of deployments. Of course, we had to redesign our antenna to be optimized for a very specific type of lakes. And this is the final design. What you are seeing here is the beam pattern and how independent it is with frequency. It's just the gain that is changing. The other big criteria for us was depth of the lake, because there can be standing waves between the antenna and the lake bed. And we wanted any kind of spectral ripples, first of all, to be less than a millikelvin. And at the same time, the ripples would be much smaller than the 21 centimeter signal. So taking all of that into consideration, we basically chose the sites. And in this talk, I would basically be discussing the deployments. But before that, we had to validate the system. So given the antenna itself, we generally don't calibrate in situ. We characterize its transfer functions externally through a very carefully designed measurement setup, through which we can reach down to around 1 part in 10⁻⁶ a sensitivity of the transfer function of the antenna. And this is what they look. So essentially what we are interested in is the beam weighted sky, which is TF, which is the beam weighted sky. And this is basically multiplied by 2 different transfer functions here. And what I'm showing on this plot are the transfer functions themselves. So the most important one is this black line, which is the total efficiency of the antenna. So it's the fraction of the foreground power that actually couples into the receiver. And just for comparison, the dotted line is what we had got when we had deployed this on the land. So one can clearly see the advantage of deploying on water, which is the efficiency itself was enhanced, which is a great thing. But at the same time, the spectral structure that we had seen was completely vanished on lakes. And the second transfer function that I just showed this system for is the S11, which basically determines the kind of internal systematics that we have because of the standing waves. And that also was verified to be maximally smooth with no embedded ripples on them. And this is the kind of validation we need to qualify this system for 21 centimeter science. Once we had all of this, we put down the entire system and replaced the antenna with the standard terminations that mimicked the properties of the antenna. And we basically ran it in the lab and made sure that we are able to reach down to millikelvin sensitivity with a maximally smooth function. So basically not fitting for any kind of wiggles and making sure that our system response continues to be spectrally smooth. And once we had achieved that, we went ahead for the second round of deployments. So this occurred in 2020, in around January to March. We deployed at 2 different sites, resulting in around 80 hours of data. And fortunately, the entire duration corresponded to very quiet ionospheric conditions and very quiet wind conditions too. Actually, we wanted to observe for longer, but then COVID lockdown happened. So kudos to all the team members who were there in the last batch, who had to, on a very short notice, close down everything and return back. But with that data, we basically ran it through our entire analysis pipeline, making sure we do not introduce any spurious features on the way. And I'd not get into the details of this, but it really involves a lot of RFI flagging as usual, along with double differencing and bandpass calibration. Once we have done that, we basically select the actual observations that we are going to use for analysis. And then we time average the entire data to form a single spectrum of the sky. And finally, we correct also for different additives that are added from the water and also from the LNA, or the low noise amplifier. With that, this is the final data that we have used. So out of 80 hours of observation with very stringent flagging conditions, we were able to get down to 15 hours of data that we have finally used. And these span over 10 to 17 hours in LST. Given the RFI environment, it is really not a very quiet radio locations per se. So we were only able to use between 55 to 85 megahertz, out of which was basically corrupted by a lot of interference. And we have basically validated this entire pipeline by running the same thing on the simulation data that was convolved with Saras beam, and made sure that we were able to go down to the noise levels of the simulations itself. And these are the final corrections that we had applied, which is to do with the efficiency of the antenna as the first term, the internal additives because of the reflections in the system. And the third is the contribution from the water itself, because it's at ambient temperature. After applying all these corrections, we get this blue line. And just for reference, the red line is without these corrections. So all the analysis that I'd be talking about would be done on this finely corrected and time averaged data. So this is our final spectrum. And the question to ask is the blue dashed line, which is the edges profile, is it present in here or not? And in order to do that, we also need a model to represent the foregrounds and any residual systematics that we might have. So we tried 2 different techniques, the Bayesian evidence and Bayesian information criteria. And we asked 2 different questions. The first is with log-log polynomials, which is what we typically use for foreground representation, how many orders do we need to represent our foregrounds and any residual systematics? And the second question is, do we also need to include edges signal in it? So basically that is shown as the joint versus poly. So poly basically just has the foreground representation, and joint model also includes the edges signal. So the 2 things that stand out are we need a 6th order polynomial to represent the components in our data. And at the same time, once we reach the noise levels, which is really at 6th order, we find that we do not need to include the edges signal at all at a pretty good significance. And the residuals that we get just after that foreground fit are consistent with just Gaussian thermal noise, and which is really the second plot right here that is shown. So with that, just for quantifying this, if we do a joint fit with a log-log polynomial, along with a scale version of edges, so basically if we do not require a joint model, the scale factor should be 0 or consistent with it. And if the flat profile is in there, then it should be consistent with 1. And as expected from these plots itself, we find the scale factor to be 0 at around 95% confidence. And therefore, we disfavor the presence of the best fit profile that was detected by the edges collaboration. And then we have to go a step ahead and explore the entire parameter space. And for this, we really thank edges collaboration for providing us the MCMC chains.
2 minutes.
Sorry?
2 minutes. 2 minutes.
Oh, I thought this was a 20-minute talk.
It's 15 plus 5.
Oh, okay. Okay, thanks.
For the question.
Yeah, I'll try to hurry up here. We acknowledge the Edge's collaboration for providing us the MCMC chains that covered the 99% confidence of the parameters of the flat profile itself. And we basically ran through our the entire set of signals through the same analysis. And we found that the entire parameter space was actually ruled out with Saras observations with different levels of the significance, primarily determined by the amplitude of the flat profile itself. Then the next is basically quantification of errors. And we are combining our statistical error that is governed by just the thermal noise, along with the systematic errors. And in order to ascertain that, we take two different approaches. The first approach is basically looking at the uncertainties in our corrections themselves and trying to see how sensitive our scale factor is with those corrections. So this is a plot that shows the recovered scale factors for different kinds of corrections, and that represents uncertainties in them, which also includes the case of applying no corrections at all. And what we find is that for all these things, the scale factor is again consistent with 0, and the kind of scatter that we see quantifies the systematic error associated with it. And the second source being just looking at the RMS for different orders and trying to place an upper limit on the level of systematics that we might have. And the last test that was done is to do jackknives. So asking the question of how sensitive we are to a specific realization of the noise. So we divided our data into 4 different sets, later half and the first half of the observation times, and also just the even and odd time samples. And again, we find that the scale factor corresponding to all of them is consistent with 0. And these are the residuals that we get for different kinds of jackknives. And the last part of my talk, which I'll just quickly go through, is doing a more direct cross-correlation between the two data sets. So we know that a flat profile might not be a unique solution, and people have written papers over different kinds of signatures that explain the data equally well. So the question was just about the spectral distortions in the measurement of edges, and do we have the same kind of spectral distortion? So this is a more model independent test. So we process edges and Saras data through exactly the same model. And on the left are the very oversampled residuals of the two. And what we do is just cross-correlate the two. And we get a cross-correlation coefficient, which is very consistent with no spectral distortions in Saras. So the two histograms basically show from Monte Carlo, if we had the same spectral distortions, we would be consistent with the blue histogram. Otherwise, we would be consistent with red. And we basically find that our cross correlations, again, are consistent with the red histogram, which basically shows, again, that the spectral distortions are not present in Saras data. And with that, I'd encourage everyone to go and check out these different papers that came out in support of Saras 3 analysis results. And I'll just skip over and go down to my summary, which is saying that currently we have been able to rule out the profile, but our next steps are to redeploy this with more integration time and radio quiet locations to basically go down to the levels of the standard cosmological models and put constraints on them. With that, I'll stop and take questions.
Thank you very much, Saurabh, for the talk and for keeping on time. So I'll invite now everyone to put questions on the chat, on the Slack channel as well, even for later, and on the Q&A. But seeing that Raul Monsalve is already with his hand up, I'll pass the word to him.
Okay, thank you very much. Congratulations, Saurabh, on this result. It's great that we are reaching these levels in terms of the experiments and in terms of the discussion. So I have 2 questions, but if I only had time for one, it would be, well, if your measurement is not significantly dominated by systematics, then we would expect that over a 30 megahertz range, you would be measuring essentially the sky spectrum, and we know that it's dominated by foregrounds, and in which case it should be pretty well modeled by 2 or 3 parameters. So how do we go from 3 parameters to 8 parameters? What do you attribute that to, and how can you be confident in that interpretation?
Right. No, great question. And yeah, so we carried out an analysis with the simulation data along with the beam of Saras. And if we are just only foreground terms on this measurement, we really need fourth order polynomial and not sixth order polynomial. And so basically this model that we have adopted right here, which is a sixth order, not just models the foregrounds, but it also models the residual systematics. And that basically is the description in the data. Now going to this part, the second part, in order to see what kind of residual systematics might be, we have basically looked at our estimations of the antenna efficiency and the additives in the system. Through basically night-to-night variations and also through a lot of lab tests. And we find that the kind of error bars that we do actually have the errors that are consistent with requiring orders up to the sixth order to go down to below millikelvin levels. So therefore, the short answer is that yes, with just foregrounds, we need fourth, but with residual systematics, we do need sixth. But at the same time, with that order itself, we have the sensitivity to detect the flat profile if it were there.
Okay, thank you. Do I have a question for another?
I think we still have time for one more question. Yeah, go for it.
Okay, thank you. Yeah, so it's a general qualitative question. Do you think that a less than 2 sigma detection, especially or report, especially when you consider all the range of the edges, possible signals, is that, how significant is that? And you mentioned that in your jackknives, all the jackknives that you do report a value consistent with 0, but some of them probably are also close to being consistent with 1. So do you? Sometimes you have said that this is a very conclusive result. How conclusive do you really think it is?
Right. So yeah, so when we explore the entire profile, we find that we are strongly dependent on the amplitude itself. So just this plot itself kind of shows how the significance changes across it. And the other shortcoming is really the frequency band itself, which also determines a lot of the significance. So to that, I would say that right now we are only limited by the integration time. So the numbers are all out there, but we definitely would want to carry more observations and not just do more jackknives, but also cross-check at other sites as well. So currently our plans are to actually this summer deploy in much quieter locations and much longer in observation time so that we have a better handle of the kind of trends that we have seen in here.
Thank you very much.
Thank you. Thank you, Saurabh. Thank you for the nice work and talk. And I think we move on, and I will move on to Jaiden Cook. Share your screen. And I'll also give you 2 minutes for the questions.
No worries. Can you see my screen?
Yeah. Yes, and it's now in full screen. Yes.
Awesome. Cool. All right. Awesome. Hi, everyone. My name's Jaiden Cook, and I'm a second-year PhD student at Curtin University. Today, I'm going to be talking about the first paper which has been submitted of my work, which is investigating the contribution of extended radio sources to the EOR power spectrum. So I'm just going to give a very brief summary of EOR in 21 centimeter. So EOR is a period in cosmic history where first stars, galaxies, and compact objects reionize the predominantly neutral hydrogen intergalactic medium. And we can probe this period in cosmic history using the redshifted 21 centimeter spin flip neutral hydrogen transition line. However, the current generation of radio interferometers is not sensitive enough to directly image these structures. So instead, we're more focused on studying the statistics of the signal by measuring the power spectrum. Here in the figure on the left, we have an example simulated 21 centimeter fast redshifted EOR signal where power is just millikelvin squared megaparsecs cubed. And on the x-axis, we have the spatial scale, which is just per megaparsecs. And so we can probe the power spectrum by using radio interferometers. Radio interferometers are useful because they naturally measure the correlation between two stations. So here we have an example of the Murchison Wide Field Array, which is the interferometer that we use at Curtin. This is a 256 element interferometer. You can see an example of one of the tile stations here. and it operates at low frequencies, which are within the redshift range that we're interested for probing the Epoch of Reionization. And so the visibilities that these measure correlate spatial scales on the sky with two antennas, and the distance between these antennas is associated with the spatial scales that you can probe. And so, however, the visibilities are not just sensitive to the 21 centimeter signal, they're also sensitive to all the intervening foreground sources, which is why we're here today. And one of the mitigation strategies for that is to observe fields that contain relatively few bright intervening foreground sources. So here's an example observation of the MWA EOR field 2, where the MWA primary beam response for the tile at the attenuation level of 10 to the -3, shown with the black contours. You can see the side lobes, and the main field of view, where the primary beam is mostly sensitive to, is shown in green. And as you can see here, it's off the galactic plane, which is this black smudge, and these dark blue circles are just extragalactic sources. So there's very few bright sources in this field. However, away from the main field of view, there are lots of bright extended radio sources, in particular galactic plane supernova remnants, which you can see actually intersecting the side lobes. And these can have brightnesses on the order of 1 to thousands of Janskis. So their apparent brightnesses can be up to 1 to 10 in aggregate Janskis in total. And then we have Centaurus A, which is at these redshifted 21 centimeter frequencies, about 4,000 Janskis. This is significantly bright. And not only that, they're in highly chromatic parts of the primary beam. As you can see on the color bar axis, this is the beam spectral index. So this is just the log difference of the upper part of the bandwidth to the lower part of the bandwidth. This gives you a first order look in the faded overlay at how much the beam changes. And in fact, at some parts of the beam, it has polynomial-like structure that gets imprinted onto these extended sources. So in the previous talk, having smooth continuous foregrounds is important. Well, foregrounds are smooth and continuous, but the beam in parts higher varying structure with higher order polynomials, log polynomials that can contaminate and cause leakage into the power spectrum. So the goal of this work is to determine the impact that these extended sources have on our ability to detect the redshifted 21 centimeter signal with the MWA for this particular field. And there are two primary sub-goals. The first being to model the morphologies of Centaurus A and galactic plane supernova remnants using existing MWA images, and then to simulate MWA observations of the EOR2 field visibilities by creating a pipeline and then estimating the power spectrum of these visibilities and comparing it to the 21 centimeter power spectrum. So first part of that is the morphological modeling. I'm not going to go into all the gory details. If you want to know any specifics, I'm happy to answer questions on Slack or during the question time. But here's an example of a particularly bright supernova remnant. This is a 200 megahertz MWA gleam image of Puppis A. Gleam was just a all-sky survey conducted with MWA. And on the right, we have a 41 component Gaussian model. So essentially, there is a comprehensive catalog of all the known galactic plane supernova remnants. And this catalog is called Green's catalog. It's publicly available online and it's periodically updated. It contains information about the RA in declination position, as well as the major and minor elliptical size and the spectral index and expected 1 gigahertz flux density of all the known galactic plane supernova remnants. We can use this position information to get cutout images from Gleam using the Gleam cutout image service, which is also publicly available online. And then using the size of the known supernova remnants, we can create masks of these images and then perform peak detection on those masked images using a Python package called ScienceKit Images that just finds features. And then you can fit Gaussians to those components using SciPy, curve fit, or other fitting algorithms. And that's what we get here. We apply a similar technique to modeling Centaurus A. However, Centaurus A is much larger and covers a larger dynamic range of angular scales. So here on the left, we have the real MWA image from McKinley et al. 2021. You might recognize this from the cover of Nature Astronomy. We break this into a set of different images of the northern outer lobe, southern outer lobe, the inner lobes, and the northern middle lobe, where instead of masking these with known sizes of these features, we instead applied some flood fill algorithms and then applied the same to generate the masks, then applied the same peak detection and fitting methods. And on the right, you get this 61 component Gaussian model that covers really large scales quite well and really small scales, but doesn't get all the fine, highly varying structure. This model is decent. It incorporates it's about 90% of the total flux of the actual image, but it doesn't need to be perfect to test the question posed at the start of this talk. So the next step is, once you've got these morphological models and their associated spectral models, is to run them through the simulation pipeline. Again, I'm going to give a brief overview of the pipeline, but if you want to know the gory details, happy to answer those questions. So this is just a flow chart of that pipeline. Essentially, this just takes a sky model cube, which is a function of the direction cosines L and M and frequency, Fourier transforms that as a function of L and M to get the true visibility cube, which is a function of UV and frequency. We can then sample that true visibility cube using the MWA UV distribution for a snapshot observation, along with a kernel which is derived from the MWA primary beam. And this effectively is the simulation of your observation once you add thermal noise. You can then grid those simulated visibilities and Fourier transform those with respect to frequency to generate, and then you can spherically average and cylindrically average that to generate the 1D and 2D power spectrum. So those are the tools that were developed in the paper. The next part is the methodology. How do we test this question? Well, we looked at specifically 2 example observations of the MWA EOR2 field. The first one has Centaurus A positioned in the side lobe. That's the same observation I showed at the start of the talk. And the second has it shifted to a null. So this is just an hour and time shift. It's the same beam projection. And then we created a series of partial sky models that didn't have Centaurus A and had varying fractions of the total absolute amount of supernova remnants. So we could test how much needs to be theoretically subtracted in order to get to a level where you should be able to detect the 21 centimeter signal. And here are the 1D plots for both of those observations. So we have the 1D power spectra for the side lobe on the left and the null observation on the right. The black squares with the dashed line are the total supernova remnant sky model plus Centaurus A. The green triangles, the solid line, are just all the supernova remnants, that's the total. And then the orange diamonds and the blue solid circles are approximately 10% of the absolute flux of all the supernova remnants and 1%. The purple dashed dot line shows the expected 21 centimeter signal plus the noise. And here for the side lobe observation, you can see that you really need to subtract at least, well, definitely Centaurus A, but at least up to more than 90% of the absolute flux of all of the supernova remnants really to retrieve the signal. It's a similar story, but slightly different scenario for the null observation. Clearly, Centaurus A doesn't contribute anywhere near as much as it did in the side lobe observation. However, you still need to subtract quite a significant amount of flux from the supernova remnants, but not quite the same amount to retrieve the signal. And importantly, a recent LOFAR paper looking at excess variance in their power spectra found a similar result with bright sources Cygnus A and Cas A in their wide field side lobes that seem to cause leakage as well. So that's good for this paper, but it's bad for EOR.
2 minutes.
no worries. I'm wrapping up now.
Brilliant.
In conclusion, Centaurus A definitely needs to be subtracted from the visibilities for EOR2 field observations, and at least a significant amount of the supernova remnant flux also needs to be subtracted from the visibilities. But this varies depending on which observation and what supernova remnants are in your side lobes. Thank you very much.
Thank you very much, Jaiden. I think now we have time for 3 minutes for questions. Please raise your hand or put questions in the chat or Q&A or Slack. Any questions? We have a sleepy audience today. Well, not for you because you're in the other side of the world.
Yep. I do feel a little bit sleepy though.
There is a question from Piana, from Boom.
No. Oh, no. Now Mario Santos has one. So I think, wait a second, Mario. I think I may allow you to speak. Yes, wait. I think you can now speak.
Oh, all right, thank you.
Yeah, Almala is better this way.
I was trying to write, can you hear me?
Yep.
I was trying to type it down and it's getting a bit long. Yeah, I mean, okay, so what does this mean for, low resolution EOR experiments like here? I mean, you're not going to be able to model the instrument itself. So is the proposal that you get some external model and then propagate that through any other instrument? Is that good enough?
That's a good question. That would be interesting to test. So at the moment, these models aren't quite ready for other instruments because when I fit them, because I use my own method for the fitting, they're still convolved with the PSF response. So I don't have deconvolved model parameters for these models yet, but that is in the works. So when that is ready, that would be interesting to test for other instruments to see if that actually makes a difference.
There's another question from Gerald Melema. Does all the Centaurus A actually fit inside the null?
Okay, I've got an image for this. So here is, these are the apparent sky model images. The right is the null observation. So it doesn't perfectly fit in the null, but it does fit. But I should also mention that that part of the primary beam changes quite a lot with frequency as well. So I haven't actually looked at just the Centaurus A sky model and how that compares to the 21 centimeter signal, because you still might not be able to detect it. Because if you look at this plot, it's a huge difference between having it in the side lobe of the null, but that gap, that's 10 to the power 6, that probably still not significant, but it would be interesting to see what the difference is. I hope that answers the question.
Hopefully, you can also guys chat on the Slack channel, in the dedicated Slack channel, and cool. I think we should move on.
No worries, thank you.
Okay, hello, can you hear me?
Yeah, I lost my info. Yeah. So,
hello?
And now we can move on. Yeah, I can hear you. We can hear you.
Yeah, great.
We now move on to speak from Tsinghua University.
Switzer. Yeah.
Switzer. Oh, sorry, it's the other way around. Switzer from Tsinghua University, telling us about identification of low intensity radio frequency interference machine.
Okay, thank you. Hello, everyone. Very glad to present our recent work. I'm Sui from Tsinghua University. So today my topic is identification of low-intensity radio frequency interference with machine learning. So since you are attending this meeting, I'm pretty sure that you are all aware of the importance of radio observation. Many large radio telescopes are constructed to help us better probe our universe. But radio frequency band has already been used in many daily life communication activities. These communication activities will contaminate our data. We call this contamination radio frequency interference. So here in the middle is a study of the radio environment of a radio telescope, WMA, which is also mentioned by the previous speaker. So you can clearly see that here is the frequency range you are interested in, and it is very close to many other radio sources. So we need to use some method to deal with this interference in data analysis. So here is observational data from Tianlai radio telescope. There are two kinds of radio frequency interference in this visibility. The first one is this high intensity broadband interference, which is plotted here. It has a magnitude of it has several magnitudes larger than the normal data points, so we can simply flag it with a threshold. But there are also some very faint narrowband signals, which is much more difficult to deal with. If we cannot remove it with a single threshold, because we will lose a lot of normal data points. So we need to make use of the other properties of archive signals, like their morphology. That's the motivation of a well-designed archive mitigation algorithm called the sum threshold. So the basic idea of sum threshold is to, instead of flagging single pixels with single threshold, it flags sequences of pixels using different threshold. For longer sequence, they use a lower threshold. It's somehow similar to stack the low SNR data to produce a high SNR data. So this strategy has been proved to be very effective in practice and has been used in many radio telescopes like Tianlai and LOFA. Another popular approach is machine learning approach. There are many existing attemptings that use machine learning to do alpha mitigation. In machine learning, basically we treat alpha as features in visibilities, and then we train a neural network to detect such features. And these are all excellent works. So our work also follows these works, but we want to further explore the robustness and the interpretability of this machine learning approach. So to do machine learning, we first need to large amount of training data. So we generate data using a simulation pipeline. We first simulate visibilities using a package called Trico, which is developed by Tram's team. We use it to generate visibilities of a cylinder array, and then we add R5 signals on it. The R5 modeling we use follows the previous design of Kira's team, which contains 4 kinds of R5, which are narrowband burst, narrowbands, and broadbands and blip. However, in our experiments, we found that this modeling may be too simple in some cases, because if you look at some real observational data, you can see R5 can be very complicated in morphology. So to add these realistic features into our model, we developed a new R5 generation pipeline. So basically, we apply some operators to the previous R5 model and explained it in the time or frequency domain. Then we use this complex R5 model and the simulated visibilities to train our neural network. So the neural network we use is UNet, which has been proved by previous work to be very effective in R5 mitigation. Before I show our results, I will briefly introduce the matrix we use to evaluate the performance of our algorithm. So in this 2-class classification problem, we usually use 2 metrics. The first one is recall, and the second one is precision. Here in this, you can look at this figure to understand what they are. So basically, precision describe among all the flagged pixels how many of them are real RFI signals. Recall represent that among all the RFI signals, how many of your algorithms found. So combine these two metrics, we can quantitatively evaluate the performance of our algorithm. And here is our first result. So here, the blue dashed line represents the overall performance of the machine learning approach. And this blue point represents the optimal point. And this red star represents the optimal point we achieve using some threshold. You can clearly see that machine learning technique can improve the performance a lot. On the right, I show a sample from test set. You can see that unit can indeed produce a much more precise mask. These are very encouraging results, but we also want to study some more interesting problems like the robustness and the interpretability of this method. So our data can be influenced by many factors like the configuration of our telescope or the radio environment or the observational strategy. So for a robust algorithm, we expect it to work under different circumstances. So we want to test whether our unit can be robust under the changes of these factors. And secondly, we also try to interpret some of the behaviors of our unit. So to do so, we designed a very simple experiment where we generate two datasets with different alpha intensity. So for the first dataset, we configure the alpha intensity to be around the signal to noise ratio 1. And for the second, we configured it to be 5. Then we train two models separately on these two alpha datasets. And we run a cross-validation of these two models. This is our results. In this figure, I show the performance of the two models applied on a SNR1 test set. And here the yellow curve represents the performance of the unit trained on the same alpha model. And this blue curve represents the performance of unit trained on a higher intensity alpha model. So clearly you can see that there is a gap in the performance. This gap is caused by the discrepancy between training data and the test data. So you can also see it in this sample. You can see that neural network trained on a higher intensity data cannot detect low intensity alpha signals. So this can cause some robustness problems, and it is also a common issue when we deploy our model into real application. So to deal with this robustness problem, we use a technique called transfer learning, which is also used by our previous work. The idea of transfer learning is very simple. Basically, we use some data from our test sets and input it into our model and fine-tune the final layers of the unit. Since we are only fine-tuning a few layers, we only need a small amount of data, and this can be done very quickly. With this extra training, we can see that the performance of the unit can be greatly improved. And this also hints us that when we deploy our model, we can first fine-tune it with our target data distribution. Here, I also made a quantitative comparison between these two models. You can see here the blue dashed line represents the model with transfer training. Another thing we're trying to do is to interpret some of the behaviors of unit so that we can understand its limitations. This can be done by using a technique called saliency maps. Essentially, saliency maps are the gradients of the prediction with respect to the input image. So here we input a very weak narrowband signal and calculate the saliency maps of 3 neural networks. These 3 saliency maps can tell us how the neural network decide whether the center pixel of this image are an alpha signal. we can learn a lot from these three science maps. First, we know that UNIT has learned to make use of the contrast between the bright signal and the background to make decisions. And also, UNIT has learned to make use of these connected, connected bright signals to make decisions, just like some threshold. Also, we can see that the unit trained on a high intensity data tend to use a small range of information, which is sufficient for high intensity data, but may not enough for low intensity data. And that's why it cannot be directly transferred into a low intensity data set. And after transfer learning, this can be greatly improved. And finally, I want to show some results on the real data. So we first apply UNIT to TLICE data. Basically, we first analyze RF signals in these visibilities and generate some corresponding data sets. We use this data set to train our UNIT and apply UNIT to this real data. You can clearly see that the UNIT can indeed produce a much more precise mask. And to demonstrate the effect of transfer learning, we directly apply this trained UNIT on blends data. Blends data are very different from TLICE data in many ways. So the directly application may not be very well. But if we fine tune it with some extra data with complex morphology, we can quickly improve the performance of our UNIT. So that's all I'm going to present today. Thank you. Just leave the summary here.
Thank you very much, Sute. Any questions? Q&A. I'm now following the correct Slack channel. Any questions for Sute? Any question? Not in Slack channel either. Oh, well, if there are no questions, if there's no questions, we take a break now, and I'll see you all in 15 minutes. Let's say, well, maybe we can cut it short and do it only 12 minutes. But anyway, let's try to start at 10:05, and then soon after 10:05 we start. Okay. See you in more or less 10-ish minutes. Get a cup of coffee and see you in a bit. Right. Shall I assume that people are back from a short break? So we restart the session after the break. Can I ask the panelists to turn on, the panelists of the second part, to turn on the cameras so we can all see them. And now we're gonna have, look, if you can, obviously, if you can turn on your cameras. I don't know how your connections are, but if you can, that is always nice. So I am assuming that everyone's back from the break. Wait, can you try to share your screen? Are you able to?
Yes.
Okay. So we're going to have Michael Pagano from McGill telling us about accounting for uncertainties in the low frequency radio sky maps in REACH, global 21 centimeter signal analysis.
Yep. So
I'll give you the 2 minutes in 10 minutes. Off you go.
Sure. Okay, so hi, my name is Michael Pagano. I'm a PhD student under Adrian Liu at McGill University, Montreal. And I'm also part of the radio experiment for the analysis of cosmic hydrogen. So that's the REACH experiment. It's a global 21 centimeter experiment. Together with Peter Sims and Adrian, we're working on modeling the foreground uncertainties for the REACH experiment. So as mentioned, this is a global 21 centimeter signal experiment. And REACH roughly has an observation window from 50 megahertz to 200 megahertz, which corresponds around redshift 28 to redshift 6. And that spans where we think the reionization and the cosmic dawn signal should be. So REACH analysis this is a forward model experiment. So we forward model everything. The antenna beam and foregrounds are both forward model. And as far as the forward modeling of the foreground goes, there are really two components here. Should remind you that the foregrounds are mostly due to synchrotron radiation, which make them very smooth as a function of frequency. And that means they can be well characterized by this power law, which itself, this equation here at the bottom, is characterized by the power law index, beta. So beta, this is the spectral index, which varies as a function of position on the sky. That's the map you see here in the top right. And then there's the base map. So the foreground base map, just the amplitude of the foregrounds at a particular reference frequency, U0. And our foreground model just takes that base map, so it takes the temperature, the amplitude, foregrounds at that reference frequency and extrapolates it according to the spectral index, spatially varying spectral index. So I should mention that the forward modeling of the foregrounds really entails forward modeling of these two separate components. And previously, it was shown by Dominic Eloy a few years ago that you could model the spectral portion of the foregrounds in a computationally feasible way by splitting the spectral map into these different regions, each region with a uniform spectral index, and then fit for those spectral indices within the REACH Bayesian framework. So that's what you see here on the left. This is an example of that, where the spectral map is split into 3 uniform regions and then 6 at the bottom. And then on the right, you see here that this model allows you to faithfully recover the true 21 centimeter signal inside the simulation, which is represented by the green curve. The red lines, so the red curves, are your observation data with your fitted foreground removed from it. And the blue lines are the reconstructed 21 centimeter signal. So you can see in a variety of different situations, this model is actually quite effective at recovering the 21 centimeter signal. But we also need to forward model the T-base portion that I told you about earlier. And so we're using as our base map the GSM that's top left. But in principle, you can use any all-sky map for your foreground analysis. The important part to note here is that these foreground maps, none of them really have any associated error bars with them. So likely when you're taking your observation data will contain some noise, and that's represented by the map on the top right. And you're trying to fit that with noiseless map on the top left, and likely there will be some errors, some residuals at the bottom. And so you can imagine that a small bias or a large enough error can lead to biasing your fits for the 21 centimeter signal, or worse, make it impossible to recover it. And that's what I'm going to show you in the next slide. This is an example of that. So that's what's happening here. On the left and right plot, I've just introduced a uniform bias on the amplitude of my base map to the level of 10 to the minus 1%, as well as 1% error on the right. And remind you that the red curves.
Michael, we lost you for a split second, so I'm going to ask you to just go 10 seconds and speak again.
Yep, sorry about that. My internet connection's a little unstable. But so this over here, we're just introducing a uniform bias in the foregrounds. So I'm just going to change the amplitude of the foregrounds uniformly by 10 to the minus 1% on the left, and then 1% error on the right. And again, the red curves are your observation data with your foreground removed. And you can see that just this little bias in the mean of the amplitude map in the amplitude is enough to, on the left, bias your recovery signal. And on the right, make it impossible to actually recover your 21 centimeter signal. So this is a problem, obviously. And what we need to do is we need to modify our foreground model. And we're going to do that by modifying the T-base portion of our foreground model. And what we're going to do is we're going to introduce these different masks represented by these MI terms, which are just going to split our foreground base map into different regions. And in each one of those regions, we're going to assign this multiplicative factor, these AI terms, which I'm going to call amplitude scale factors. And these scale factors will roughly just adjust the temperature in that region of the base map. And then these amplitude scale factors are then fit for within the reach Bayesian framework, the way that you would fit for any of the other parameters. And for now, we're just going to assume spectral, we're just going to assume that our spectral index is uniform. So we're trying to build some intuition here of what these amplitude errors can do to our signal recovery. So for the time being, we're just going to assume a single spectral index in the sky. And then, well, we have to decide how we're going to define these regions. So starting with an error map on the top left, what we can do is we can bin those errors, we can bin the temperature, and then map in each one of these different regions associated with these vertical bars that are demarcating the range of the temperatures in each one of those regions. We can just map them to the regions in the sky, which you see in the bottom left over here. And we use this with percentiles, so you can split up the errors from the 25, 50, 75 percentile, for example, if you like, or you can use some other binning procedure. And so the elephant in the room here is that I mentioned that we don't have a priori the errors of the foreground map. So part of this work is really just about studying the different scenarios we could have for these foreground errors. And they range from the bottom, more uncorrelated errors, function of position, or the other extreme on the right, in the top map over here, where the errors are correlated. So part of this work is to really look at all these different scenarios. And what we've done is we've picked out what we believe to be the most realistic error scenario. And this involves taking the absolute errors of our foreground map, computing the fractional errors, and then from the power spectrum of those fractional error maps, draw an error realization that you see here at the top. Put that into our data over here at the bottom. And the next few slides, I'm going to show you the results of fitting this noisy data with our noiseless foreground map. And there is no 21 centimeter signal in the simulation. So the green line here is at 0 because I have not included any actual 21 centimeter signal. And without any amplitude scale factors, you can see that this is basically going to fool our analysis into thinking that there's this 21 centimeter signal recovery in blue that is not there. And that is a very big problem. With the introduction of scale factors, one scale factor, so this is the same observation scenario, no 21 centimeter signal in our data. One scale factor basically just adjusts the mean. That's not good enough. We still have the systematic on the left. 3 amplitude scale factors, still systematic. And then finally at 5 amplitude scale factors, you can see the regions here are on the right and the recovery plots are on the left. 5 amplitude scale factors is able to actually pass the null test. But you may ask, I stopped at 5. In principle, I don't know that there's no 21 centimeter signal inside my data. And so why stop at 5? I can go to 6, 7, 8. I can go all the way to 12, for example. And that's a problem, right? We don't want to be in that overfitting regime where we can introduce as too much complexity into our system, too much flexibility into our model, such that we can fit literally anything. That we should avoid. And our answer to avoiding that is to use the Bayesian evidence of our model in order to pick out which or how many foreground regions are optimal to describing this data set. So what we're going to do, so Bayes' theorem here on the top, posteriors on the left, likelihoods, the prior and the denominator is the Bayesian evidence, the probability of my data given my model. And what we're going to do here is we're going to plot the log evidence as a function of the number of regions I've included in my map. And then we're just going to select the model which maximizes that Bayesian evidence. So we're looking for the preferred model to explain the data. And that corresponds to region number 5, which is the plot that I showed you in the previous slide. So of course, you can continue adding extra regions into your data, into your model, but the Bayesian evidence will suffer because they're not really required to explain that data set. So at that point, you're just hurting the evidence. So we can stop at 5 and avoid this overfitting scenario. This is a case where the previous slides have showed you are a case where there's no signal and there's only a single spectral index, which is not realistic. In reality, there might be a signal and there is spectral complexity in the sky. So we have to reintroduce these beta terms, spatially dependent beta terms, and then add signal into our simulations. But I want to point out on this slide is that the spectral regions and the amplitude foreground regions don't need to coincide. They can be completely different. They don't need to be correlated in some way. The regions could be deduced completely differently. So to keep in mind that the way that we split the spectral part and the amplitude T-base are in principle different. But those signal recovery plots, those picking the model which maximizes log evidence, now turns into a two-dimensional grid because I have scale factors in the horizontal axis and I have the number of beta regions, the number of spectral regions in the vertical axis. And now instead of picking on a 1D plot, which model maximizes the evidence, I'm looking on a 2D grid. In this case, this is going to be the 2 regions for scale factors and 10 spectral regions. So I'll show you some of the key recovery plots here. Nothing special about these models, just picking different regions of the map to show you what the signal recovery looks like in these regimes. On the bottom left, you can see that there's, for 1 amplitude scale factor and 6 spectral regions, there's still a bias. And then at the top, you can see that 9 scale factors and 20 spectral regions, there's still a bias. And the model which maximizes the evidence is actually 3 amplitude scale factors and 10 spectral regions, which gives us this fit. And you can see that the 1 sigma lines are consistent with the, of our fits are consistent with the green true signal. And I should note that, yeah, sure. And I should note on this slide over here that the number of scale factors, at least 1 is always required in order to fit the data set. So the log evidence over here, you can see that this is thresholded at 230. This is thresholded at the smallest value. And for those values, you have recovery plots which don't at all, aren't at all able to recover the green true signal in the plot. And you can see that for 0 amplitude scale factors, I have just a lot of cyan. So in other words, I have a lot of models that just are unable to explain the data set. And that means that I can't fit amplitude fluctuations in my error map using only spectral regions. So I can throw up to 25 spectral regions, and yet that is still insufficient in order to explain the noisy foreground maps in T-base. So we could also move into an LST dependent fit. So typically Reach uses this LST averaging where it takes the observation times and adds them all together and averages out. But we're moving in a direction where we're going to fit at each LST independently. And in such a scenario, we can still apply this formalism and we can still pick out the maximum evidence model, which over here is N4, NA is equal to 4. And in such a scenario, we end up with our most true recovery plots, or nicest recovery plots over here on the right. You can see that the green line exactly fits our models. And so this is applicable into different schemes, in this case, applicable into LST independent scheme. And with that, I'll take questions.
Thank you very much, Michael. And any questions? Any questions from people? So actually, while people are either typing questions, also if you want, you can request and I can unmute you, and you can make your question, and you don't have to type. But while people are typing or even doing those requests, I was wondering one thing on your is that you're trying to fit. You create your forward model of the foreground, and you try to somehow fit that forward model. But that's before you add the H1 signal, right?
Sorry, so can you repeat that then? That's before I add the true signal?
Yes. So
that's right. So the data set is created with true signal inside it, and as well as these amplitude errors. And then that's being fit for with your base map with these adjustable amplitude parameters, which can scale it.
So I think my worry is that when you then, okay, so you kind of try to calibrate a model with simulations, but then when you compute the power spectrum for the, in your case, for the EOR, I assume, I'm not sure which frequencies reach works, but based on frequencies you're looking at, I assume the EOR, when you compute the power spectrum, do you propagate those errors into your estimates of the H1 power spectrum of the EOR?
So in principle we do, but we don't really compute. So as part of this analysis, we're not really computing the, we're not fitting the power spectrum. We're fitting the temperature in the sky is what we're doing. But in principle, if you were trying to fit the power spectrum, you'd have to propagate those errors.
Yeah. Anyone else? No hands up. Oh, I think people can make more questions on Slack. Oh no, Raul. Yeah, and with yourself.
Thank you very much, Michael. Can you hear me?
Yeah, I can hear you.
Oh, okay. So when you produce simulated data, can you give some details about the data that you produce for the first half of the talk? In other words, what kind of LST beams and what noise levels? And how do your results for that part of the talk, at least, depend on the noise level that you assume for the measurements?
Yeah, so noise level in our data set, correct? Not in the foreground?
Right, yes.
Right, so we've done this for, so the first part of that question, we've done this for 1 hour observations times, and those are 61-minute integrations. We've also done this for 6 hours with 360 integration times, so 1 minute. And our results are quite robust. So it doesn't really depend, like we have, I should say, our model is effective in both regimes. And then as for the noise level, we've tried adding random Gaussian noise to our data set at a variety of different levels, which in the reach analysis is actually fit for. So I believe the fiducial amount that we're adding is 0.25 Kelvin, random Gaussian noise to our observation data. In our LST dependent fits, so when we're fitting at each LST independently, because we have more snapshots of the sky, we're not averaging everything together like we are in an LST independent integration. In that situation, to be clear that we're adding proportionally, as far as sample variance goes, more noise, like 0.25 Kelvin times root n, the number of integrations we have. So really at this point, like our noise model is quite simple. I know Harry's on this call and he's involved in making more complicated noise models, but right now the one that we've considered is just random Gaussian noise at 0.25 Kelvin in our data set.
Thank you.
Thank you, everyone. Thank you, Michael. Thank you for the really interesting talk. And now we move on. And I'll ask Erin Bosco, Joanna, to share the screen. Elimboto is from the Dar es Salaam University College of Education in Tanzania. And Elimboto, can you share your screen? And then mute. Not sure if we have Elimboto on the call. Yes, okay. Yeah, I wasn't supposed to be seeing myself. But we have it. That's good. I think, Elimboto, you need to share a different screen, or you need to bring your presentation to the screen you're sharing. You needed to bring it to the foreground. All right, now we have your talk, yes. Can you unmute?
Yes.
Okay.
Oh, all right.
So we're seeing the PDF, but I think it's fine. It's fine. You don't have to go to the full. If you can go to the full screen, be nice. Otherwise,
Yeah, I want to put to the full screen model.
Be somewhere
Oops.
on top.
Yes.
Cool.
Yeah.
Brilliant, brilliant. So we now have Elimboto Ioana from Dar es Salaam University College of Education telling us about recovering the 21-centimeter signal from simulated fast intensity maps. And now if you go.
Okay, thank you guys. So as I've been introduced, I'm from the Dar es Salaam University College of Education. This is a constituent college of the University of Dar es Salaam in Tanzania. So I would like today to present about how to recover the 21 intensity maps. That's fast telescope maps, simulated maps by using PCA. Yeah, some information is cut.
Okay, so
the approach, yeah, the approach
it's
that
a bit zoomed in somehow. For some reason, I
yeah, I don't know why, but when I was checking my desktop, it was looking quite well. But okay, I'll try to present to you. So we know that H1 intensity mapping techniques is very robust approach in surveying large-scale structures of the universe. And actually, this is an opponent of galaxy survey, which focuses on individual galaxies. Instead, intensity mapping focuses on surveying a large patch of sky volume. So it has the advantage because it can produce biotomographic maps of neutral hydrogen atom emission distribution present in the universe over a large range of angular scales. This also provides a sensitivity to baryonic acoustic oscillation feature over resistive ranges inaccessible to current galaxy surveys. We know that it is a good trace of galaxy distribution. And then once we have information about 21 centimeter signal, we can use them to constrained variance cosmological parameters, for example, dark energy question of state. In the modeling that I've done with PCA, with fast telescope, these are parameters that we have used. They compose of instrumental and maybe we may refer them as we go on later. So the focus is to recover the 21 centimeter signal, the theoretical one as being okay.
Limbo, sorry to interrupt you. I'll give you the time. Don't worry. I think if you look on the top, there must be, instead of full screen, there must be something called presentation
signal. And then you will see the modeling could recover this signal. And we have patches of skies that have a frequency range from 1050 to 1450 megahertz. I don't know, it's happening. Yes. Yeah, so that this 21 centimeter signal that we are looking for is buried under a lot of under very huge contaminant in
think we may have lost the Limbo. Limbo, are you still on the call? So look, let's move on, and if Elimboto manages to return, we go back to his talk. And if you don't mind, I would ask Haochen Wang from MIT to present now. And in the meantime, I'll try to speak with Elimboto to see if what's going on. Is that okay, Haochen?
Yes. So could you allow me to start my video and share my screen?
Okay. Let me.
Great.
Okay.
And I'm going to share my screen in just a moment. So can people see the slides or just my desktop?
No, we can see your slides, although we can see the top bar.
The top bar.
Yeah.
So
probably also have to go into presentation mode, but can you go to the next slide?
Yes, let me try it again. Let me see if I can go to my next slide. Can people see this?
That's fine.
Okay, great. So let's start.
Let me present you first. So we have now Haochen Wang from MIT telling us about a systematics robust 21 centimeter foreground removal algorithm. And off you go. I'll give you 2 minutes warning in 10 minutes.
Great, thank you. So hello, everyone. My name is Haochen. I'm a PhD student at MIT. And today I would like to present a new systematic, robust foreground removal algorithm, which aims to remove foreground residuals by cross-correlating filtered data. So in this talk, I just want to show the very basic idea of the algorithm. But if you're interested in knowing more details, please check out our paper, which just came out on our archive earlier today. So let's dive in. The problem we try to resolve is the systematics-induced foreground residuals. For example, let's just start by considering some simulated visibilities. So what you see here right now is the visibility of the true H1 signal produced by a small antenna array through simulations. So this is what we expect to see if our foreground filter were to work perfectly. However, when we try to estimate the H1 signal by passing the simulated data through a foreground filter, we found that very disappointing that the visibilities are oversaturated by foreground residuals. So this is because the bandpass errors were present in the simulated data, which the filter failed to account for. So in this simple example, we actually used the Cahunen-Loewe filter, but that doesn't really matter because we know all the filters break down when systematics are introduced. So this is really independent of what linear filter we use. We're always going to see a lot of foreground residuals. So apparently, we want to remove the residuals in order to recover the signal. And to figure out how, we notice that the power of the residuals is dominated by the true foreground power and weighted by some perturbations due to the systematics. So since the foreground leakage here contains information on the systematics, we can naturally draw out the systematics by cross-correlating this with the true foreground, as now shown on the left-hand side. And of course, you might say that we don't actually know the true foregrounds. That's true, but since the foregrounds are so much brighter than the signal, our instruments can essentially measure the foregrounds to very high signal-to-noise ratio. So this means that we can actually cross-correlate the estimated foreground with the, we can actually obtain a very good estimate for the foreground. So then we can just cross-correlate this estimated foreground with this estimated signal, and that should be able to draw out the systematics. So that's a very basic idea. And now let's illustrate this idea with a toy model example. So in this simple example, our data is just a sky map as a function of frequencies and pixels as indicated by the index nu and p. And the data consists of three components, the signal, foreground, and bandpass errors. These components all have different dependencies on frequencies and pixels. Since this is a toy model, we just naively assume the signal is completely uncorrelated in both frequencies and pixels. And we assume the foreground to be independent of frequencies. Again, very unrealistic, but just for the simplicity for the toy model. And last, the bandpass errors by definition only depends on the frequency. So given this simulated data, our goal here is to implement the idea from the previous slides to estimate the systematics and to remove the foreground contamination. So before we can perform a cross-correlation between the estimated foreground with the estimated signal, we must have basically estimate them first. And this is quite simple to do in the toy model. So since the signal and bandpass errors depend on frequency, but foregrounds don't, that means we can simply estimate the foreground by averaging the data over the frequency as indicated by this bracket. And then to estimate the signal, it's even simpler. We just need to subtract the estimated foreground from the data to obtain an estimated version of the signal. And just like what we saw in the simulated visibilities a moment ago, the estimated signal is dominated by foreground residuals, which is proportional to the product between the true foregrounds and the bandpass gains. So now we can cross-correlate the estimated foregrounds with the estimated signal. And we do so by summing their product over the pixels. And this is because the pixel axis is precisely the subspace that bandpass errors act on. So to see very intuitively why this formula can give us an estimate for the bandpass errors, we recall that the estimated foreground here is dominated by the true foreground, and the estimated signal is dominated by foreground residual. Therefore, on the numerator, we essentially have foreground squared multiplied with the bandpass errors. So we normalize it with another foreground square in the denominator, and that draw out the systematics, which is the bandpass error. And now, with the gain error estimated, we can now use them to subtract the foreground residuals and obtain the recovered signal denoted by S tilde here. So in previous step, we already have an estimate for the signal. It contains the true signal, but very unfortunately dominated by this foreground residual. However, we also just obtained an estimate for the bandpass errors as well as an estimate for the foreground. So we can remove them by subtracting this term off, and that leaves the true signal. So that was the very basic idea, but for a very simple case. And now let's talk about a more realistic simulation. So we actually simulated a 5x5 compact antenna array of 6-meter dishes, very similar to a setup you see on the right-hand side. So this is actually the Tone telescope at Green Bank Observatory, which serves as a prototype system for the CHORD and HIRAX experiment. So we also simulated a sky map and feed the map to the telescope and produce visibilities as data. So to process realistic visibilities with our algorithm, apparently we have to generalize the formalism quite a bit. So for example, we have to use more sophisticated linear filters to estimate the foreground now that it is frequency dependent, and we will have to account for mode mixing and estimate for the gain errors. So I will leave all those details to the paper, but the very basic idea of cross-correlation presented in the toy model is still the same. So first, we just use the bandpass errors with a variance of 10⁻⁴ as telescope systematics. And here I'm showing a plot of the angular power spectrum. The x-axis is the multiple L, which indicates the angular scale, and the y-axis shows the magnitude of the power. So first, we plot in blue the input power spectrum that we use to generate the H1 signal in the sky map. And the green data points here, you see, they show the power of linearly filtered data before we subtract the foreground residuals. So compared with the blue curve, we see that due to systematics, there is foreground bias in the linearly filtered data, and the bias is at 1 order of magnitude. And then you see in red data points, that's linear filtered data after we have performed our foreground residual subtraction algorithm. And you can see that compared with the data points before our algorithm, after the foreground residual subtraction, our algorithm successfully removed essentially all the foreground bias and is able to recover the input power spectrum. So now we move on to increase the bandpass error by 1 order of magnitude and repeat the analysis. And this time we see a more catastrophic foreground bias of roughly 3 orders of magnitude in the data before we're performing our foreground residual cleaning algorithm. And once again, our algorithm, after subtracting the foreground residuals, is able to remove essentially all the bias in most bins. So that works very well. Then we continue ramping up the difficulty for our algorithm by using antenna-dependent complex gain errors as a systematics. So complex gains include multiple components such as bandpass errors, delay errors, and random phase errors, therefore much more challenging to estimate. But our algorithm performed well nonetheless. So again, we started by setting the amplitude of complex gains at the 10 to the minus 4 level. And our algorithm essentially successfully removed all the foreground bias, just like what we saw in the bandpass case. And when we increased the amplitude of the systematics by another 10 times, we finally start to see some foreground residuals remaining after our cleaning algorithm. This is mostly because the complex gain errors are much more difficult to measure due to its large degrees of freedom. But this nonetheless shows an improvement of 2 orders of magnitude when compare the signal after foreground residual subtraction with the data before this algorithm. So essentially, our algorithm is still able to improve the results. So in addition, thank you. So in addition to the promising results that have already been shown, there are still lots of room for further improvements and generalizations. First, even though we only demonstrated the algorithm on removing antenna gain errors, the algorithm can actually be used to estimate any parametrizable systematics and remove their induced foreground residuals. This means the algorithm can be easily extended to other systematics like baseline errors. And we are also thinking about how to apply this to non-parametrizable systematics. The basic idea of cross-correlation is still valid, but the details are still under development. And second, in our demonstration, we used the Calhoun-Loewe filter to produce estimated signal and foregrounds, but actually any linear foreground filter can work as well. And last, in our current algorithm, we only subtract foreground residuals which are at the first order in systematics. We could, in principle, calculate foreground residuals that involve second order terms in the amplitude of systematics and remove them as well. So to conclude, we have developed a systematics robust foreground removal algorithm that estimates systematics by cross-correlating the filter data. And in simulations, our algorithm achieves a 2 order of magnitude improvement for certain types of systematics. And finally, this family of algorithms where you can cross-correlate the estimated signal and the foreground to draw out contamination has the potential to ease the requirements on telescope collaboration for 21 centimeter surveys by orders of magnitude. So that concludes the talk, and I'm happy to take questions from the audience.
Thanks, Haochen. So any questions for Haochen? No? Any questions? Well, what people are typing. Maybe I can make a question. Oh no, there's one question from Arnab Chakraborty. Did you check the power spectrum as a function of K parallel over delays to check the signal recovery or lost signal?
Yeah, so in current study, the power spectrum is only computed as the angular power spectrum. So in principle, we could check the information about the signal loss. But here, what actually we can do to control the signal loss is through, basically, it can be done analytically. That's precisely because we first apply a linear foreground filter that makes this algebra a little cleaner for us to actually write down how much signal and how much foreground we're removing, basically as a perturbative expansion in terms of the signal to foreground ratio, as well as the amplitude of the systematics. So in other words, yes, we could perform we could calculate the power spectrum in K parallel and check it by other means. But in this analysis, we do that by actually perform an analytical calculation. Yeah.
we have a question in Slack that I'll ask you, Haochen, to also answer writing, but since it was written, it's from Isabella Carucci. What are the systematics that you do not expect to be removed by this hybrid method? You mentioned certain kind of systematics in your summary slides.
Yes. So basically, when I say certain types of systematics, it refers to, as we go back to the previous slides, basically all parametrizable systematics. So when the slides I showed the bandpass errors as well as complex gain errors, and other parameterizable systematics will also work, like the baseline error. And what might not work? So first, we haven't directly applied this algorithm to non-parameterizable systematics yet. That includes systematics that will be difficult to parameterize due to the large degrees of freedom. For example, beam error can be very difficult to deal with because it's hard to write it as in an analytical way in terms of different parameters, because it has just too many degrees of freedom. But in principle, we can extend this algorithm to deal with like beam error as well, because even though it's hard to write down, like in terms of a matrix, how beam error will transform the data, we can nonetheless estimate its effect through basically either empirically or through simulations. And the idea of draw out the effect of systematics by cross-correlating the estimated signal and foreground is still valid in that case.
Yeah, thank you. Any more questions to Haochen? We already passed the time. 2 minutes. Well, there's no more questions. Unfortunately, we couldn't have one of the talks. We're gonna speak with the organizers, so Elin Boto can upload his talk recorded, so everyone can watch it at a later time. So I'll close the section now. I thank Haochen and all the other speakers for being here this morning, well, in GMT, and presenting their work. Thank you very much, and we'll all reconvene at 3 p.m. later today. Thank you, and bye-bye.